Okay, everyone, so we're going to just do the last major concept before the exam that's coming up on Wednesday. And the conflict sign-up will be due on Monday night, and I'll post it tomorrow. So the conflict's at 4:30, as usual, and anybody who wants to can sign up. All right, so analysis of variance. That's what we're going to be doing, and you're probably wondering, wait a sec, haven't we been doing analysis of variance all along? Well, yes, we have been doing analysis of variance, that procedure of dividing the variation of the y variables into two parts. One that's explained by the model and the other that's left in the errors. We're going to do the same thing here, but in a specific situation that people call ANOVA. So it's confusing because this word ANOVA refers both to the situation of comparing group means and to the whole procedure that we've been doing all along of splitting the variance of the y's into two parts. So basically what we're going to do is we're going to extend the two-sample z or t-test to more than two samples. So back in Stat 100, we tested hypotheses for the average in two populations using a two-sample z-test or a t-test. And the null was that the population averages were the same, even though in our sample they might not be. For example, we might want to look at the exam scores comparing males to females. And we did a two-sample z-test. But let's say we wanted to do three groups. Let's say we wanted to compare males, females, and some other gendered category. Or let's say we wanted to compare, instead of two ethnic groups like whites versus Asians on exam scores, let's say we wanted to do whites, Asians, Hispanics, blacks, etc. We have more than two groups. And when we often want to compare three or more group means, right? And it's the same exact thing. We can't boil down the difference between the groups into a single signed number. We can't just say the observed minus the expected, because the difference between the two groups. We have three groups, four groups, right? So what do we always do? We always square. We always square the differences to eliminate the signs, and then sum those square differences. And so it's what we've been doing all along. So it gives us a statistic that's the ratio of sums of squares, the ratio of two variances. It's the F statistic, or the chi-square statistic, that we've been using all along. So you're going to see the same thing that we've been doing all along in a much simpler context. So that's what we'll do. So the main idea is this analysis of variance procedure we've been doing all along that breaks up the variance of the y's into two parts. So the sum of squares total, how spread out the y's are around their mean, is broken up into two parts. The sum of squares model, plus the sum of squares error. Okay? That's what we've been doing. And in regression, we said, okay, so we predicted some y variable. Let's say it was final scores, final exam scores, and we predicted it based on some regression line, slopes of the regression line. We had quantitative x's, like exam scores, homeworks. That's what we did. So we had a regression line, and that was our model. And then the spread around the regression line was our error. Now let's say we wanted to do the same thing, let's say even with final exam scores, but we didn't have quantitative. We're not comparing we're not building a model with quantitative x's. Let's say we wanted to predict people's final exam scores based on their ethnicity, for example, or based on their sex, or based on some kind of, whether they're in the in-person, online, or some other. If they're just in two groups, we can do a two-sample z-test. But if we have more than two groups, we are going to predict, we're going to have a model based on the group means. It's basically like stereotyping, right? If you're a girl, we're just going to say that's all that we think about right now, and you're just going to get the average. Our best prediction for you is the average for girls. If you're a boy, our best prediction is the average for boys. If you're some otherly gendered, that's our best prediction, the average of them. It's just seeing if we can do any better by basing our y variables, the variance of the y's, on group membership. So it's just the sum of squares, they call it. The model is there any difference between the group means? Like if we're doing ethnicities, is there any group difference, a significant enough difference between any of the groups, between whites, blacks, Asians, Hispanics, whatever we have, that will help us predict some quantitative y. And then compared to what? Well, there's going to be differences in these group means, but we're going to compare it to like the error, which is the within group spread. You know, if there's a huge amount of within group spread, that membership in that group is not going to be very accurate. So that's the idea. But these are exactly the same thing. And the statistic is exactly this is a specific case of regression, and we're going to see that later on. So we've got the same everything. You have the it's the same statistics. All right, so let's look at it in the context of an example. All right. So let's say, I just want to give you a simple graphic, visual. So let's say 2 experiments were done to compare the effect of 3 different drugs. We have 3 groups, group A, group B, group C. Drug A, 3 people took drug A, 3 people took drug B, and 3 people took drug C. That was in one experiment, we got these results, and let's say in another experiment, we got these results. So, all right, so we're comparing 3 means because we're always with ANOVA measuring quantitative responses to the drug, like duration of the illness, not whether or not someone died, not 0, 1 variables, right? We're not measuring that. We're measuring quantitative responses. Okay. So let's look at this. So in experiment 1, 3 people took drug A, and the mean of these 3 people, their responses on some quantity, how they, duration of the, some response to the drug, quantitative response, and the mean was 1. Okay. It was 1.5, 1, and 0.5 for these 3 people. And here the mean was 2. These are called the group means. And here the mean was -3. And you can see that the people did within each group, they came very close to the mean. Right? And what is this here that I put here? The grand mean. What that is across here, and it doesn't have to be 0. That's the mean of all 9 numbers here. So it's the average of these 9 numbers. It's the overall mean. It doesn't have to be 0. I just drew it that way to make the math come out easy. It can be anything. Okay. And then, let's say that was experiment 1. Now let's look at experiment 2. We got this, let's say we got the same exact mean. So the mean response of those 3 people who took drug A was 1, same as it is here. And the mean response for these 2 groups, 3 people, was 2. But look, this person got a 7, this is a -3. There's a lot more spread here. And the mean here is still -3. Okay? So we have, so these are the 2 experiments. Now, what I want you to just intuit, and why don't we do this as an eye clicker? Just think, we'll get out the eye clickers, is this problem A? In which experiment does it look to you like there's stronger evidence to reject the null? I mean, the 3 means are the same. So let's just answer that question. Let's go to the eye clickers. So this one says experiment 1 has stronger evidence for at least one of the drugs being different. Forget that thought, it's a typo. Experiment 2 has stronger evidence for at least, experiment 2 has stronger evidence for at least one of the drugs being different. And both experiments yield the same evidence because the 3 drugs have the same means in both experiments, so will tell us the same thing. So choose A, B, or C. And just look at the graph, and let's say you got these results. Which one looks like there's more evidence that the drugs are really different, have different, okay? Or at least one of the drugs is different. So I'll give you just a minute, and then I'll stop it. Okay, and let's see what you chose. It's the answer is 1. That experiment 1, and people were pretty close, weren't sure. They thought maybe experiment 2. So let's think about it. Let's go to the document camera here, and let's write that down. So, in which, to me, it looks like there's stronger evidence to reject the null, that they're all the same. Like here, there's so much overlap. Everybody overlaps each other. Here, it looks like 3. This drug, group C, really looks different. What if every single person had the same response? Every person, even though the means were 1, 2, and -3 for all of them, what if every single person had the same response? I'm wondering if you got fooled because this is scaled differently. This is going from -10 to 10. So I'm not sure why you got fooled. But anyway, what if every single person who took this drug, everybody's got the same response? And these people are really spread out, each one of them. Don't you think this gives you more evidence? Do you see that? Take it to the extreme, that there's no within group variation. So if you take this drug, everybody gets exactly the same response in all of them. And here, even though they might have the same means, let's say the spread was enormous. Wouldn't you think you don't really have evidence here that the drugs are different? Does that make sense? Nod if it does. Okay, good. So experiment 1 gives you stronger evidence to reject the null that, what's the null? It's right up there. That all in the population, the mean drug response is the same. And the alternative is at least one of the drugs is different. So what I want you to do is compare. Look at the spread between the group means. How do the 2 experiments compare? They have the same exact group means. So they are the same. Both experiments have the same group means. That's the sum of squares. That's a measure of the sum of squares between. The sum of squares between is going to be the same. But look at the spread within each group. That's the error. How do the 2 experiments compare? Experiment 1 has much smaller error. And we call that within group spread. And so that's measured by the sum of squares within. It has much smaller error. That's a measure of our error. Okay? And what the f-stat does is it compares the differences between the groups to the differences within the groups. And if the null is that the group membership tells you nothing better than the overall average, well then that statistic should be about 1. The way it makes sense that it would be about 1. Right? It compares the amount of variation between groups to the amount of variation within. Under the null, if no difference between the groups, we'd expect that ratio to be about 1. If it's significantly larger than 1, we'll reject the null. Okay? All right, so that's pretty much the idea. Here's just another intuitive way to think about it. And now, maybe we should look, let's see, let's go to the next page. And before we do this page, why don't we just skip to the summary, the next page, the Chapter 3 summary, and then go back to this. So let's look at our Chapter 3 summary. Okay? And what does it say here? It says, in this Chapter 3 summary, that ANOVA for comparing group means is just an extension of the two-sample Z or t-test for 3 or more samples. Okay? We're just extending it. But it's also a special case of regression where the predictor variables indicate group membership and the group means, or differences between the means, take the place of the slope. And that's why we can use the exact same statistics that we've developed before. It's just a special case of our general ANOVA model. So why don't we write that down here? So basically, and we'll look at why that is. We'll translate it into a regression equation on this next page, previous page. So let's look at this. This ANOVA, when we're comparing the group means to see if any of them are different. Is really just a linear model, or a regression model, a linear model, like we've been doing all along, with categorical X variables. They're not quantitative, like they have names, like are you black, white, Hispanic, whatever. They have names to them, they're categories. Predicting a quantitative Y. We've actually done that before. In fact, we did something, we've done that before. A binary variable is a categorical variable. We've already done that. That's why this is going to be, but this is when you only have a quantitative, only a categorical variable. And we're just going to look at the single case where we have one categorical variable broken up into multiple groups. So what can we do? So an example is, like, we can write it as a linear model, right? That's what we're going to do. So let's do our example we just looked at. So those 3 drug groups. So we can write it as a linear model. By doing what? And we'll do it in a minute. By creating a binary variable for each group. So there was what? There was group A, B, and C, right? That's what we were doing. Just take one of those experiments, just one of them. So, so it would be like, we'll say group A, and it'll be 0 if you're 1 if you're in group A, 1 if in A, 0 if not. And we'll do the same with group B and group C. Okay, so let's do it on the, we'll do the same exact thing, these binary variables. So let's do it on the, this will be 1 if in B, 0 if not. This is an if. 0 if not. And this will be 1 if in C. 0 if not. Like we've done before, right? So that's what we do on our previous, let's just do it. Okay? So that's what we're going to do right here. All right. So we're just doing this example again. we can rewrite our previous example with 3 binary predictors, 1 for each group. 1 if in group, for each one. And let's see, we could fill these right here in with the correct slopes. So this is just one, these are all 1, 0. So if you're in group A, it's going to be 1 for this group, right, and 0 for these two, right? I'll write it again. And we'll do it for each one. So it'll be 1 if in B, 0 if not, and we'll do the same here for C. Okay, so let's say somebody is in the group A, one of those, people in the group A, right? What their variable will be 1 here, and these two will be what? They'll have a 0. They're not in B because they're in A, so won't they have a 0 here? And they're not in C because they're in A, so they'll have a 0. So these will disappear, and if they're in group A, that's just a 1, and our best prediction for their mean response is what? Just the mean of group A. We'll do it in general. It's just, and we'll call that mu for group A. Does that make sense? That's the slope. So now let's say they're in group B. If they're in group B, we have a 1 here, and what is A? Isn't that a 0? So these two will disappear. That's just a 1, and their predictive quantitative response is the mean for group B. And similarly here. So that is our linear model. It's just a linear model. These are x variable and x variable, 3 binary x variables predicting 1 y variable. And we could say, how many parameters do we have? We have 3 parameters. So we're going to do the same thing we always do with the number of parameters equal to the number of groups. So note that with ANOVA, when you're comparing group means, it's an easy way to remember this, the number of parameters, P, when we do our degrees of freedom, is going to be equal to the number of groups, in this case 3. Here it will be 3. Now there's a more usual way that people write it. You don't usually see it. This is the easiest way to interpret, but there's a much more common way for people to write this. Usually, one group is chosen as the baseline, and its mean is used as the intercept, because you're looking for differences between the groups, so it's an easy way to test for that. So usually one group is chosen as the baseline, and its mean is used as the intercept. And then the other groups are represented with these binary predictors, and their slopes are expressed as differences from the baseline. So let's fill in the blank with the correct slope if you using what? Group A as your baseline. And we're just going to look at that. So if group A is the baseline, that means the intercept here is what? This right here is just going to be mu A, right? So when A, and this is still the 0, 1, so when you're in group A, you're not in B, and you're not in C, those disappear. So that makes a good prediction for you. That predicts the mean of group A for people in group A. What happens if you're in group B? Well, what if we did our usual thing and just put mu B here? What would happen? That's our average for B. Well, this is a 0, 1 variable still. These are still 0, 1. So this is 0 if in B. Whoa, 1 if in B. 0 if not. Sorry about that. And this is 1 if in C. 0 if not. It's just 1, 0. Okay, so we've got that. And so now when you're in group B, that cancels out. But now is that going to, and this is a 1, is that going to give us the right estimate? No. So what should we do? We need to subtract off A. So that would be our slope, the difference between those two. Then we get, this is 0, these subtract off, and we get GB is a 1, and we get the right mean for that. How about if you're in group C? If we just did C, well, this turns to 0, because you're not, this is a 0 for everybody not, if you're in C, you've got a 0 for B, but now you still have to subtract off group A. So that the slopes, where did I say that? The other groups are whose slopes are expressed, and this is the way you'll usually see it. So if you have 3 groups, you just have 3 minus 1, 2 slopes and 1 intercept. See, this is written without an intercept. So that's another way to think of node again. Even if you write it this way, it's even more like you have 3 parameters still, and 2 slopes the way we usually do with an intercept. It's still equal to the number of groups, because you have an intercept, you have 1 intercept plus 2 groups. Right? It's still equal to the number of groups. All right, so this is, I'm just trying to stress, I think that it's useful to just have one formula for everything and one way of visualizing everything. So now you don't have to remember a lot of different things. You just know that it's still our usual formulas, and now everything's going to work out the same. Just remember that the number of parameters is the number of groups. And if you write it this way, it looks very much like our regression model. We don't have to bother doing that. Okay, so now let's work out a problem. And what we're going to do exactly, I'm trying to make it exactly like what we did with regression. We're first going to test for the overall difference with an F or a chi-squared, and it will be the same exact thing. And then we're going to look at the individual group differences, and we'll use a Z or a T like we did with the individual slopes. All right, so let's look at this. So what are we going to do here? All right, just trying to think. All right, we did this before. Okay, so the null hypothesis is this very simple model that all the group means are the same, all of them. Okay, so you might as well just predict y from the overall y. So if we were looking at our exam averages and we thought what ethnic group you were in made no difference, we'd say we'd just predict, we might as well just use the overall mean for everyone. That would be our best prediction. Knowing which ethnicity someone is tells you nothing about their exam scores. Sorry. So, do you understand that? Do you understand how what we're doing here? All group means are the same in the population. We see some differences between them, but they're not significant. And the alternative, which is the more complicated model, is no. We can do better if we predict their quantitative variable, their final scores, by their group membership. So, if you're white, predict it by the average that the whites got, something like that. At least one of the group means in the population is different. So they don't all, we're testing that at least one is different. The null says all of them are the same, so the alternative, as usual, is not all of them. So at least are the same, at least one, there's at least one group difference, pairwise difference. So does using the group means to predict a quantitative y make a significantly better prediction of y than just using the overall mean? That's all we're doing here. This is the same as asking, does it reduce our prediction errors significantly? So we're doing just like we did before. Remember we did this with regression? We said the sum of squares total. This is the first step towards taking a standard deviation. So if these were final exam scores, however many, let's just do it here. So we're going to do example 1 here. So we have these drug responses. We have 3 groups, group A, group B, and group C. All right? And we had these responses. So it's just this is just the observed, these are the 9 observed points. So these are the observed y's minus their average, minus this overall mean, which is the average of the 9 points. So when you're going, the sum from I equals 1 to 9 in this case, because there's 9 groups. So we're going to sum these 9. We're just looking at the sum of squares total of these 9 groups, which is for each one, we're just going to subtract off their overall average. So this is just the mean overall, or grand mean it's called. And then square them, okay? And then we're going to break them up into 2 parts. One part that's due to the model, so we can do it like this, like we did before with our line. And we said one part that was due to the model was just our predicted based on group membership. So in this case, it would just be that little, this 1 right here. How much better that does than the overall average. The difference between that, then the 2 here. And then the -3. These distances, and you can see if we just summed them, 1 plus 2 plus -3, we'd get 0. So that's why we don't do it. Then we subtract off the averages. And after we subtract off the average, if we just summed them, we'd get 0. So we have to take the square. Okay? And where that's going to be, so let's write that down. So this is our predicted with a hat, our predicted y's. In this case, predicted y's is the same as what? The group averages, because that's what we're predicting. That's what we're saying is our best prediction. So that's the group averages. That's what that is with a hat over it. And this, of course, is our overall average. So it's this distances here, and then we're going to square them. Then we have the errors, which is just our observed for all the 9 points. This is our observed minus our predicted, minus the group mean. So let's just get a visual of that. And then that's these. How far off, like 2.52 is how far that is from 2. 1 point. It's very little. See these little ones. And what ANOVA does is it compares your model, the blue, the ratio of that, to the yellow here, to the error. And if that's large enough, you'd expect it to be about 1 when when the model's no better than the error. So that's the idea. And let's work it out. Okay? So let's do all that. And you can do it right here. By the way, the reason why, let's just draw the picture for the other one. The other one, the model, was the 1 from 0 to -0 and -3 minus 0. But look at this error. We had this huge error. So it's like that overshadows the differences between the groups. All right. So now for experiment 1, let's calculate all this just like we did. Remember when we did the same exact thing for simple regression with 3 points, how far they were from the line? I'm doing exactly the same thing just to refresh your memory if I can. That was like, we did that. Yeah, I'm even coloring it the same way. I just want to show you it's the same thing. Now, this is what we're doing. We're doing the same thing. It's just this is linear regression, and now we're doing it with a much simpler case of just means. This is much harder. Okay? This is just a special case of that. All right, so now let's do this. So so let's just do it. So we take all the 9 points and we're subtracting off the average. So let's do this. So we don't get lost, I'm going to say minus 0 squared 9 times. That's 3. Whoops, I already messed up. Damn. Sorry. So let's just do 1.5, 1, and 0.5. Now let's do the next group. I should have written what? 2.5 here. 2.5 minus 0 squared. So here you have minus 0 squared and minus 0 squared. And then I'll have 3 more. All right. So now I should do 2, I'm right here, and 1.5. And now I'm finally here, and I have negative 2.5 minus 0 squared, negative 3, and negative 3.5. Oh, such a mess. What did I get? Do you really want me to work all this out? You don't want me to write all these down, do you? Raise your hand if you do. I could. They're very easy. Do you want me to? Raise your hand if you want me to write them all down. Raise your hand if you don't want me to write them all down. Thank you. Okay, so I did sum them, and I got 43.5. Okay? The first one, for example, is 2.25. And the last one I got down here was 12.25. And you just do them all through. All right, so that's for now. We're going to break it up into 2 parts. All right? So let's do that. And this part is this is this one. Right here. Okay? So for all 3 points in this group, their predicted is the same. It's what? 1. For all 3 of them. There's 3 of them that have 1 as their predicted, and for those 3, and we're just subtracting off the average. Okay, so for all these 3, can I just say 3 times because there's 3 of them, what is their predicted for all these 3? Their group mean, which is what? What's their group mean there? I'm going to make it bigger. 2, 1, and negative 3. Those are our group means, okay? So for these 3 points here, they're all going to be the same. I don't want to have to write them out each time. So they all have what? 2 as the predicted minus 0 squared. We're going to add all these together. And for the next 3 points, what's their predicted? Negative 3. And then we have minus 0 squared. So we'll add all those up. This is 3. This is 12. And this is 9 times 3 is 27. We add all those up, and that's 42. See how much that explains almost everything? Our error should be what? What do you think this is going to end up being? 1.5. Let's just figure out, though. It is 1.5. So now what are we doing? Now we're taking our observed minus our predicted. Okay, so let's look up here. So our observed minus our predicted. For this one right here, that's where we are, observed minus predicted. Okay, so we have, for this group, our observed minus predicted. Okay, so 1.5, the predicted is 1. And we're going to square this. Plus there's 1 minus, wow, that's right on its predicted, the middle one. Doesn't have to be, but it is this time. And the last one is 0.5 minus 1 squared. So those are those 3. And now we're going to just do the same with this one. So this one is what? 2.5 minus 2 squared plus 2 minus 2 squared plus 1.5 minus 2 squared. And then our last group is the same here. And they don't always have to have the same spread exactly, but they do here. And our last group is what? Negative 2.5 minus negative 3. So that's plus 3 squared. And then we have plus negative 3 minus negative 3. So that's plus 3 squared plus negative 3.5 plus 3 squared. So if we add all those two, these are all the same. This is like 0.5 squared plus 0.5 squared, so that's 0.5. This one's equal to 0.5. and these 3 are equal to 0.5, so it checks out. Sorry. It's very tedious. Very tedious. Somebody was telling me they had to do this in one of their classes, and there were a lot more points than this. It's very tedious. But that's the idea. Any questions? I think it's really good to know what you're doing to do it, but to do it, and you're going to be doing it for homework. So this is your homework. You're going to be doing this experiment right here. You're doing the same exact thing. That was the homework that we didn't get to this last time. So this is on the homework that's due Friday. So this right here, you're going to do the same thing for this experiment. All right? Now what we're going to do is put this, now that we did all these calculations by hand, without being given any r squared, we actually did this. So we're going to have to, let's put it into our ANOVA table and calculate the f. And that's on the next page. Okay. So here we are. And let's fill this in. So we had our sum of squares total 43.5. This was 42, and this was 1.5. Now our degrees of freedom. G minus 1, right? And remember, I put it here. Once again, the ANOVA table is a handy way to illustrate how the sum of squares are partitioned. And you can make the model one of two ways. You can think of the model as just with 3 groups like this, or as an intercept with 2 groups. Either way, there's how many parameters? 1, 2, 3. 1, 2, 3. So either way, it's 3 parameters. So that's, and G is P. So here we have, they call G minus 1. It's the same as P minus 1. So number of parameters, I'm writing it again, equals number of groups. Remember that. Then you don't have to, number of parameters equals number of groups. Then it's just like P minus 1. This is the same as P minus 1. This is the same as N minus P. And this is N minus, it's just what you're used to. Okay, so we have 3 groups. G is equal to 3. N is equal to 9. What else do we need? That's it, right? Okay, so we have 3 minus 1 is equal to 2. N is 9. So n minus 3 equals 6, and this better add up to n minus 1, and it does. It does, so it checks out. All right, now we do the same thing. 42 divided by the mean square model, or the mean square, sum of squares divided by the degrees of freedom, and we get 21. And here we have the sum of squares within divided by its degrees of freedom, and that's 0.25. And then to get our F ratio, what do we do? It's the ratio of those two. So it's 21 divided by 0.25, which is 84. And that should jump out at you as a huge F, because remember, when the null is true, we should expect about 1, and look what we got. Now, the standard deviation of the errors, which features in a lot, and it's going to, you see this a lot. It's a measure of the error of each group. That is the square root of the mean square. So it's going to be the square root of 0.25. So that is 0.5. Now, from this, we can actually, r squared wasn't given to us, but do you know how we can get r squared? Remember, the model, remember, this is SST, right? This is r squared times SST, and this is 1 minus r squared times SST, right? So r squared is just going to be, so r squared is always just our sum of squares model, sum of squares between, sum of squares model, right here. It's the ratio, it's the proportion of the total that we can explain by the model. 42 out of 40, the variation 42 out of 43.5 is explained by the model. So it has a very high R squared. I'll just leave it like that. All right, now this is what you're doing for homework. Here it is. I'm not going to do it for you. So this is your homework 12, last problem. Due Friday. This whole part. Okay, so you can do that. And now, any questions? All right. Let's turn the page. So now here is an example from our own data from a previous semester, and it's on a scale of 0 to 10, this was Stat 100 data, rate where you fall, where 0 means you strongly favor gay marriage and 10 means you're strongly opposed to gay marriage. And so then people also identified their ethnicities. This was from Stat 100. And so here's white, black, Hispanic, Asian, and mixed and other. We broke it into 5 ethnicities here. And so now we want to look, and we see these averages here. And the question is, are there differences between ethnic groups? Are these differences significant, or do they just are they just due to random variation? One way to think of it, there's 2 different ways, and we'll look at both of them. You know, one way to think we'll do now is to think about a wider population and say, okay, these were sampled from a wider population and use our parametric statistics. Another way to think about it is, what if we randomly assigned people these ethnic groups, randomly paired up the ethnic groups with their ratings? How likely would it be to get this kind of differences? And that's a re-randomization test. So we'll do both, but we only have time to do the parametric one today. Okay, so it looks like there's substantial differences. Look at this one compared to this one, looks pretty big. Can we predict a random person's attitude towards gay marriage better by using the group averages than we can by using the overall average for everyone, regardless of ethnicity? That is what a significance test is asking. So the correlation between the predicted ratings based on ethnic group and actual ratings is this. This is our R. That's fairly low. But is it high enough? I mean, you might not care about it just because this is really pretty low. You might not care about it. But is it big enough to be statistically significant? That's all a significance test answers. It's not whether we would care about it. Any difference, no matter how small, will become statistically significant, no matter how insignificant it is to us practically or whether anyone would care about it. We're just talking about statistical, and we have a big sample size here. But okay, so what are we going to do? So it looks from here. All right, so we'll do a significance test. Now it's going to be easy because I gave you R squared. If I didn't give you R, you would have to do what we just did. For how many points? 858. Can you imagine? We did it for 9. It would be so tedious, right? But now we have R here, so we can, super easy. Okay. So, now, why don't we do this one as an eye clicker, because I want to, what's the appropriate significance test to test the null that all 5 group means are the same in the population? We just happen to see small differences in our samples due to chance. Uh-oh, eye clickers only have what, 5? You can only do 5 choices? Oh boy. I guess we just won't do it then. I'll just tell you what it is. What do you think it is? Do you think it could be a z-test? No way, because we have 5 groups. We could do a z-test with 2 groups. T-test, same thing, right? So that's any of the above. And either that eliminates all this. Now, We have 858 people. That's a huge sample size. So I think we could do either of them. So that, the only part is what eliminates that. So either 1 or 2. We don't need anything except r squared. What do we need? Let's do it. We just need r squared and n, and the number of groups. Okay, so what's the alternative hypothesis? This one we can do. Let's just quickly do this. This is A and B. So which do you think? I didn't write it up, but let's just quickly do it. See if I can go back, just go over here. Okay, so choose A or B. You get to see what people are choosing. This is fun. Oh, you see it too, though. Okay. Are you going to just go along with the group? Oh, somebody's doing C, G. Okay. All right. I'll see if I'm going to just randomly stop it at some point. You might get caught. This is hilarious. Okay. All right. You want to play? Okay. Let's see if I caught some people. Oh, that's so funny. All right. So, yes. Great. You know this one. I love it. All right. So now let's just go back to the document camera. All right. So we got that. At least one. Yes. Everybody's going to get that right on the exam. And it will definitely be on there. Okay. At least one. Now, compute the chi-squared. Okay. You know what? It's probably better for you to just take a half a minute and write down what you think like the form of it is. Like you got the R, you've got the N. That's all you need. Just write it down then you'll remember it better. You won't have to say this test is Wednesday. This will help you. You don't have to calculate it out if you don't want. You can just, all you need is this and this. That's all you need for chi-square. Okay? So, chi-squared, if I were you, I'd just say, okay, you know r squared over 1 minus r squared. If you don't know that, okay, that you know, right? And then, what are you going to multiply by? N. That's it. That's easy. So then you can figure it out. 1920 and you square it over 1 minus 1920 and square it. And then it's time 858. And see how this big number is going to make a big chi-squared here? Let's just see. 32.84. That's a big chi-squared. Because chi-squared, the mean, when the null is true, is equal to its degrees of freedom. Now, write down the degrees of freedom. What do you think it is? Degrees of freedom. Remember, it's p minus 1 always. So in this case, p is what? How many groups did we have? You have to look at, oh, there it is. It gives you it right there. There's 5 groups. Okay? So p minus 1 is g minus 1, which is 5 groups we have. 5 groups minus 1. That's the degrees of freedom, which is equal to 4. So easy to get messed up on these degrees of freedom. So, now what does it say? How many degrees? Looking at the chi-square, what's the critical value of chi-squared at 5%? So we have 4 degrees of freedom. Let's see if we can get that. Remember, doesn't depend on the sample size. So 4 degrees of freedom right here at what? 5%? So we're right there. See that? 9.49. Did everybody see that? Okay. It's much easier to ask you the degrees of freedom with chi-squared than it is without. Okay. 9.49. So that's what we've got. And that's our critical value. So what does it say? Okay, what's the critical value? So the critical value we'll put a little chi-squared critical value with 4 degrees of freedom is equal to 9.49. Our chi-squared, 32.84, is much more further out on the tail, much more extreme, so it's much greater than 9.49. So our p-value has to be less than that 5%. Probably a lot less. So we'll reject the null and conclude that at least one of those differences is significant. That at least one of the group means is different than the others in the population. All right, now you did that. So write down F now. You've got this part. Hint, hint, hint. Write this down first and then adjust it. Remember, it has 2 sets of degrees of freedom. So what is your F? I'm just going to write down that part first. Okay, you got that. You have to adjust this and this. You have to make it like that. You have to adjust something here and put something there. Remember what it is? It's n minus p, but that's the same as n minus g. And p minus 1, which is the same as g minus 1. So now we are done. All right, so we can just write that out. So that's 0.1920 squared over 1 minus 0.1920 squared. And then we have in our, what is it? 858 minus 5. So that's 853 and 4. G minus 1. And I got 8.16. Okay, it's smaller by about the amount of that. All right, now, how many degrees of freedom for the numerator? And don't make the mistake of putting that. That's what everybody does just because it simplifies to that. The numerator is our model, and our model has 5 groups. But it's the degrees of freedom is you subtract off that interceptor. Once you know the means of 4 of them, you know the last one if you know the overall. I mean, once you know the means of n minus 1 of them, g minus 1 of them, I should just shut up, sorry. 4. You know it, right? Okay, 4. And the denominator is this bigger one. Okay, looking at the F table. Okay, let's do it. F table, 4, 853, 816. Critical value, okay. The one at the back of the book doesn't even go up this high, but there's one I included earlier we can look at. This is a long chapter. It was like when we first did, right after our test. I know it's in here somewhere. I'll probably include this one on the exam. What page is it on? Oh, thank you. 97. Oh, yeah. All right, here we go. Okay, so the numerator is 4. Now, the denominator was what? I can't even remember. Okay, so it's between 500, it's in between those two. Let's just say when it's in between, the convention is going with the smaller one, being more conservative, like you don't have as big a sample size. So we will go with this, that one. What is that? 2.3898. Okay, 2.3898. So F star is equal to 2.3898. And this is for 4 and 853. But 853 was between 2 lines on table, so we just went with the smaller one. It makes it easier to grade, and that's how people often do it. Okay, I think it was 500. All right, so we do that. So we just want to compare RF. What's RF? RF, is that bigger? Is it further out on the tail? Yes. So 816 is more extreme, more weird than that. So it's going to happen less than 5% of the time. So p is less than 5%. Okay, so we reject the null and conclude at least one of the means is different from the other. Okay, now for the hard part. Oh. So fasten your seatbelts. This is hard for people to understand, but I hope I can make it intuitive. All right, so you know all this. I think this part's exactly the same. This is just the same thing we've been doing, blah, blah, blah. Okay, chapter 25. So this is the hard part. And maybe it won't be that hard for you guys. Okay, let's look at this. So now, once the chi-square and the f-test tell us that at least one of the groups is different from the others, how can we determine which ones? Well, we can do z or t tests between the pairs of the groups. Okay, this part's easy, but we have to adjust it for multiple comparisons. And post hoc comparisons mean after looking at the data. Post this, after this, but after looking at data. Okay, so let's just go through this. All right, so let's just look at this. All right, so this is what we got. That's the same thing. You saw little histograms of it. And what did we see? We saw this big difference between two of them, these two, right? So let's say we didn't know. Boy, I didn't expect a difference between those two groups. This means that blacks are very conservative on this issue, more against gay marriage. Hispanics are very much for gay marriage compared to them, okay? So we see this difference. And we want to see if it's significant. But we looked after the data. We didn't make a hypothesis ahead of time. We looked through all these, and I found the biggest and the smallest, and I said, oh, let's test this one. So that means after looking at the data. So what you have to do is adjust for all the possible comparisons. I looked through all of them and cherry-picked one. So that is basically sort of like hacking my p-value. I can't really do that. So I have to adjust for doing that. So what do? How many possible pairwise comparisons did I really look at? Well, how many possible pairwise are there here? There's just comparing two groups. So there's 5 groups. So just say so there's 5 I could take from my first group and 4 from my second one. So there'd be how many with 5 groups? So with 5 groups, there are 5 ways you can choose the first comparison. Let's say we chose whites. And then there's 4 other groups. I could say whites, blacks, whites, Hispanics, whites, Asians, and white mixed others. And I could do the same with blacks. Blacks with 4 other groups, and Hispanics. So that's 4 times 4, right? 20. But that's ordered pairs. And I don't really want to care about ordered pairs. That's counting picking whites first and then blacks. And blacks and then whites as 2 separate. So it's 5 times 4 divided by 2. So that would be 10. So in general, if you know combinations, it's 5, choose 2. So in general, though, so that's for g equals 5. For g in general, it's g times g minus 1 over 2. So for g equals 5, we have 5 times 4 over 2. All right. So we are basically, whatever p-value we get at the end is bogus. We have to multiply it by the number of possible pairwise comparisons. So let's say we found something we thought is significant. Let's say like even at the 1% level, I'd have to multiply it by 10%. So it guards against making a type 1 error, a false alarm. Do people understand that? So that's the idea. So let's go through it now. There's a lot here. All right, so what are we doing? So I want to start by comparing the Black and Hispanic averages to see if the difference is significant. So let's just go ahead and perform our usual t-test, our usual way. And what is the null hypothesis? The null is what? That in some larger population, that the average between the two groups, between the Blacks and the Hispanics, is equal to 0. And they're equal to each other. And the alternative is it's not equal to 0. There's no difference between the groups. All right, so calculate the t. So what is the t? It's our usual t, our observed difference between the two groups, which is that difference, minus the expected under the null, which is 0, over our standard error for the difference. All right, so let's do it. So our observed difference is just the difference between those two, 3.643 minus 1.848, okay? Minus 0, we have that difference, which I got to be 1.795. So that's our observed difference. Now, what's the typical variation? The typical standard error. Do you remember how to do this? You have to combine the standard error from two sources, right? You have source from, in a larger sample, you have a source coming from the Hispanic population and Black that you sampled from. Two sources. And how do they combine? They combine as, I'll just tell you, the square root of the sum of their squares. So you're going to get a standard error from the Black group plus a standard error from the Hispanic group. And when you combine it that way, it's bigger than either one of them because there's two sources of error, but smaller than the sum of them. It's like the hypotenuse. It's bigger than either side of a triangle, but smaller than the sum. So, how are we going to do that? Well, all right, we'll just do it out. Okay, so what are we going to do? So the standard error, remember? So we'll have the square root. Now, what is that? It's going to be, the standard error is going to be the SD over the square root of n for Blacks. So we go to Blacks. Now, this is makes it, you're going to like this, makes it a lot easier to do this. We are going to use this old friend we've been talking about forever, it's very important, as our estimate for the standard deviation of all these groups. You're never going to get exactly equal standard deviations here, but remember one of our assumptions is, we're doing these linear models, equal variance within each of these groups, homoscedasticity. And these look pretty good, and what we're doing here is we're using this as a pooled estimate for all of that. So we're going to use this, our standard deviation of the whole thing under the null, right? This is going to be our pooled estimate for all of it, because under the null there's no difference between the groups. So we're going to use this estimate, use pooled estimate as, use this pooled this as, that's not a good way to write it, that's confusing. We want to use the SD plus errors as a pooled estimate. Right? Of the SD plus, because we're doing a t-test for each group. And this makes it a lot easier for us. Remember that. So, that makes it a lot easier. So, SD over square root of n. Remember standard error for the average is SD over square root of n. So, we're just going to use that. That makes it a lot easier. 3.18 over the square root of what? Plus for both of them. Now, one will be Black and one will be Hispanic, so we just have to put the n's in there. That's square root of n. So we have to look up here and get our ends, 84 and 99. Okay. And I forgot to square them, right? So I better square them. You're going to like this because it makes the arithmetic so much easier. So that's our... Now we can simplify that really well. You can see we can oops, look what I did. These are not both 84. Which one? I'll put this one 99. So sorry. That would make it very easy. All right, so now we're going to simplify this. The numerator is still 1.795. Do you see how we can factor out right here? We have this here. Let me just show you. We're doing this, but here. It's easier to learn it in an example. Why am I even... Okay, so we're going to factor this out right here, 3.18, right? So we can take that, and the square root of 3.18 squared is this. So it's 3.18 over the square, and we just have ones here. Over 1 and the square root of 84 squared is 84. 1 over 99. So basically, I know that didn't look so easy to do right now, and I'm very sorry, but it really is after you think about it. So let me just give you the answer here, and I'll 1.795 over 0.4719, and I got 3.804. Okay, I hope that didn't go too fast for you here, but if it did, watch this. I go through it here, right, and just show step by step the arithmetic, okay? What I did here, I just factored out that standard deviation of the errors. And this right here is the formula that you want. This is the one we did. You would do exactly the same thing, but with the standard deviation of the errors. So, and this is the only difference with the t is you have that plus in there. This is the one we did. So that's what we just did. Any questions on that? All right, so now the very last thing is what? So we get 3.804. All right, that's our t. 3.804. Where can we put it? So let's put it here. So t is equal to 3.804. How are we going to find the p-value? We need the degrees of freedom. And here's where everything's just the same again. Everything's the same. The degrees of freedom, when you test the individual t, remember they're based on everything. They're based on, it's the same for regression. It's based on all n minus g. All n minus g points. So it's the degrees of freedom is going to be right here. N minus g, which is equal to 853. Okay? So then we just have to look on a, so let me tell you what I got for this p-value. I got for this p-value a tiny, tiny t. But now what do I have to do? I have to multiply it by the Bonferroni correction. I have to, this is where I have to say, okay, that's really a bogus p, because I really made 10 comparisons. So I have to multiply it by 10. I mean, I cherry-picked 1 out of the 10. And that will give me my p-value. So I know that was a lot to process. So this is called the Bonferroni corrected. So that's because the Bonferroni corrected p-value. That's with the correction. Now, you had a huge amount, and you know what? I mean, I'll put the homework up. Why I wanted to cover pretty much everything that's going to be on the exam, because now I want to give you all this time to study, and then when you come in on Wednesday, you have all this material, and then on Tuesday we can go over it again. That's why I wanted to. The only thing we have left to do for this is the randomization test, which re-randomization test, which we've already done for regression. We're going to do it. So we'll go over this again. You're going to do the homework. I'll put all your practice tests up there, everything up, and you can practice a huge amount. And then we'll go over it on Tuesday, and then your exams on Wednesday. So I just wanted to give you everything so you're going to learn through the homework. And through all the practice tests, I'll put them up. Does that make sense? Plus there's office hours Friday and Monday and Tuesday.